I'll go live.
Pull the trigger.
Yep. Okay, so before I start, well, first this tech talk is going to be recorded on YouTube, so if any of you like have to leave like midway or anything, you can probably just watch it like after it's done. Also, I'd like it if the questions could be kept at the end because I want to make it as quick as possible to avoid having like a super. Oh, that was feedback.
What?
To have a too long video for anyone who watches the video. But otherwise, I have the files on my GitHub as well, and there's like also the PowerPoint on that repo. So okay, so this talk is going to be on Docker and Kubernetes. So Docker is a super popular container software that's been used really frequently in a lot of companies, so it's useful to know. So that's why I made this tech talk. So we're going to go over Docker first, and afterwards we're going to go over Kubernetes, and then security in Docker and Kubernetes. That order is mainly because we use Docker images and containers in Kubernetes. And for security in Docker and Kubernetes, we kind of need to know Docker and Kubernetes first. So that's why it's in this order. So yeah, this is the classic Docker meme. So why use Docker? It's because you can just ship your whole system, basically your whole like all the dependencies and whatnot. So let's begin with specifically what is Docker. So Docker is a OS level virtualization software. So it's similar to virtual machines in some ways, but it does have like massive differences that make Docker containers preferable over virtual machines. So it allows the delivery of software in the form of packages, or rather called containers. So you can ship software that you write in code like Python or whatever, and you can ship it into containers. And those containers basically run a stripped down OS. So it lacks many components of a regular operating system, mainly to avoid redundancy when running multiple containers. And those containers are bundled with the software that you wrote, libraries that you depend on, and config files that you use. So containers can run in parallel, isolated from each other, so they don't have like they don't really share I guess a environment. So they have their own like isolated environment to run their code. So as I said, Docker is super popular because containers are really useful to have when deploying software. So its popularity has skyrocketed ever since it released, I think in 2013. So initially, all software was basically just deployed on a single OS. So this had many problems, mainly because you had like tons of dependencies and you could end up having conflicts. And it's honestly just a mess to deploy like multiple things on a single operating system. So then we have virtual machines. So in each virtual machine, we have a operating system, and we have the application running inside of it. Um, so the main problem with this, as I said previously, is that you have a lot of redundancy because you're running your operating system on top of another operating system, and there's a lot of things that these two virtual machines could share together. So that's where containers come in. You, instead of having like a operating system in each um for each application, you instead have a container runtime that can get rid of that redundancy and have only one for all applications. Um, so so yeah, so why Docker? As I said, it allows for encapsulation. You can isolate applications from each other. There's no or very little conflict between containers. You have everything you need inside of the container, so you don't need to install anything. You just have all your dependencies in the container. Um, it can be run in any machine that has the runtime, whichever container runtime you have. Um, so it's you don't have like all the issues with is this OS compatible, or like if 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 something's not compatible, it's a pain to try to make it work. So you have the Docker runtime that's already functional on that operating system or that machine, and as long as the Docker runtime is functional, then you can run the container. So yes, you don't waste time. It's super quick. And you ship containers in the form of Docker images, and you can deploy them, roll them back super quickly without having to mess with dependencies, mess with the installation of whatever application you have. And since there's no redundancy, Docker uses resources more efficiently than VMs. So Docker is super useful in the enterprise context, but it's also useful at home. So you can actually use Docker to deploy really useful containerized software into your at-home Ubuntu or Linux server. So there's a few examples. You can have a BitTorrent client that you can access through a command line, or you can access it using a web client. So for example, qBittorrent has a Docker image, Deluge has one as well. You can run a media server, so Jellyfin, MBPlex. You can also run game servers, or even home automation, or basically any application that you can think of, as long as it has a Docker image available. If it doesn't, you can actually build a image yourself. So it's super easy to deploy. So usually when you deploy a single container, sometimes you want to keep track of like the settings, the configurations that you have for a specific Docker image or deployment. So that's where Docker Compose comes in. So it's a declarative way to deploy containers. So this means you write a YAML file, and it declares all the parameters that you use to deploy a container. And what's useful about this is that you can actually version control your deployment. So you can put it in Git, push it to GitHub or whatever, and then you can keep track of all the changes you do. And you can simply deploy a Docker Compose file, a YAML file using Docker Compose up, and it's just a single command. So yeah, it's really useful to deploy single containers and also multiple containers as well. So you can actually have multiple images in a single Docker Compose file, a single Docker Compose YAML. But there's better software to do it. But Docker Compose is perhaps maybe simpler if you just want a single container. That better software could be something like Kubernetes, but it really depends on your use case as always. Um, but for a single container that you say would deploy at home, it's probably preferable to use Docker Compose. So this is the example Docker Compose. So that's actually a Docker Compose file I have in my Linux server that I use to host my BitTorrent client. So you first have the file format version. So they tend to release different file format um, specifications over time, and you kind of need to specify which version you use. You have the service name. That's the image name from the library. So Docker keeps a library of images on your system, so you can specify which image to use. If not, you can actually put a URL and have it pull the image from Docker Hub or a image repository. So you have the environment variables for the container, and you also can mount volumes into the container. So for instance, you can have your hosting system. So the host system, you can specify where you store the config files, which should not disappear after you kill the container. So that's why you need to mount it on your host system. And you can mount it into the /config folder inside the container. So that's what the volumes are for. It's for mounting folders from your host OS into the container. And that's basically the gist of a basic Docker Compose. So now we're going to move on to a quick demo of Docker. So the environment I'm using is on Windows. Maybe some of you guys don't like Windows, but that's what I use. But since you can't run Docker on Windows, you actually need to have Linux. So I'm using WSL. So that's Windows Subsystem for Linux 2, which allows you to run a virtualized Linux inside of Windows. So yeah, as I said, it's meant to be run on Windows, on Linux. And you can access WSL through command prompt, and Docker Desktop also exposes its own commands inside of PowerShell and command prompt, which is cool if you don't have WSL and you run Docker Desktop alone, but that's probably not a recommended way of doing things. So the application that we'll deploy is a small web API. So it's gonna have all the endpoints at port 8000. The app is written in Go with a dependency on a library, so this is Gorilla Mux. So the point of having dependency is that there's actually something you need to do when you build a Docker image to actually install dependencies. So this is so docs.docker.com has a useful documentation to write Docker files, but I'll actually show you the Docker file itself. So a Docker file is actually really similar to pipelines. If any of you guys wrote YAMLs for pipelines, so it's gonna use a base image. So the base image in this case would be a well, it doesn't usually it's Ubuntu, but in this case we're gonna use Alpine since it's smaller. But it's gonna be Alpine Linux image, which contains Golang. Then we can label the maintainer of the image, which is going to show up in image repositories. And then you have all the commands that you're going to execute to build the container. So you set the working directory inside the container. You copy the dependency files. So gomod and gosum contain the dependencies that we need. And now we download the dependencies and then we build the Go app and we expose the port to the outside world. So if we see here, it's exposed, it's port 8000. So if I run the Go application on my Windows system, we can see how it should function. So for this, we're going to use Postman. So Postman is something really useful to test APIs. So we're going to do it really quick. So we can send a get, and then it displays welcome home. And we have a REST API, which is at this URL, and it expects a JSON. So that expects a JSON like this, and when we send it, it should add it to a array. So that's the application. And now we'll begin with booting up the WSL instance. So now we'll start by building the Docker image. So we'll move to our directory. Oh. And I'll start by so first of all, we need to call the Alpine image. So this is so this Docker image is based on another Docker image. So we need to pull it first. And after we pull it, we can simply just build the container just like this, the image by running Docker builds. So now it's built, and we can check if it's really in our local library. So this is the library in your operating system for all Docker images. So you have a ID, and it's going to be accessible by Kubernetes, the Docker runtime, and whatever. So to begin, we're going to tag it with a name that's actually human readable instead of this hash. So we'll tag it like this. So since I do have other versions, I'll tag it 0.4. Okay. So if we go here, we can see that it has a new name and a tag. And now we can run the Docker container. Okay, I hope this is gonna work because I may have changed something. But anyways, we'll use the tag to refer to the image, and it should be running. So okay, so we have the Docker container running, and if you look at Docker desktop, you can see the name that we specified, new container. So the name is new container in the command, and in theory it should work. If not, I may have messed up. So yeah. Yeah. Wait, actually, this is not. Um. Okay, yeah. So that's. So we actually changed the port to 8080. That's in the Docker file. So if you go back, you expose 8080 to the outside world. And then we can access our application through that port. So after that, we can just quickly kill our container using its name. Oh, okay, so we can then even delete the image, but I'll just show the command. I don't actually want to delete the image, but you simply enter the image name like this and you can delete it. But instead of doing that, we'll actually just push it to Docker Hub. We can actually specify which repository we want to push it to, but in this case, we'll push it to Docker Hub. So simply do it like this, and it should be accessible at this URL. Okay. So so we can see it here. It's pushed, and we actually have all the commands we ran to build the container. So anyone can actually just come and pull this container using this command. And we'll actually try the command out. So we'll just pull this container. And it pulled, it didn't actually pull it because we actually have the image in our library. But if we delete it as I showed previously, we actually don't have the image anymore. And if we pull it, we should have it. Yep. Okay, so for this portion, this is a useful command if you need to debug. So say you want to access a container and run commands inside of it, you actually can, because it's actually kind of a stripped down Linux inside of the container. So this is the docker exec command. And if you, well, first we need to run the container actually. But you can actually run the docker exec command to go inside of the container and use shell commands, bash commands. So we're actually inside the container, and this is actually the application we have. So we went inside the working directory, and we can actually see kind of a Linux system inside of it. So we want to, it's actually not bash, it's actually Bone shell that we're running because it's a Alpine container. But say you wanted to run to use bash. So you can actually run a command which I actually forgot. So it's apk add. Well, weirdly enough, it worked, but usually you would need to run to have a root user, but okay, well this is weird because it actually works, but if you want to be root, you run this command. So docker exec -u root -it new container and so on, and now you're root. Yeah, it's weird because it works. Okay, so that's basically the how we deploy Docker image. It's super easy, and rightfully so, because that's the whole point of Docker images. But say we didn't want to install bash like this, mainly because it's not gonna actually update the image. So you're actually gonna lose bash next time you deploy the container. So we actually want to modify the Docker file. So you can simply add a line to run the package installation command. So apk update and apk add bash. And that would make your image instantly have bash instead of not bone shell, the original shell. So anyways, that's how you run a command inside a Docker file. And that's basically how you run a Docker container. I'll just bring up the PowerPoint again. So now we're gonna go quickly over Kubernetes because I think we spent too much time on Docker. So it's a orchestration system for containers. You can automatically deploy and manage containers using a set of rules that you specify. It can run automatic health checks to see if containers died and restart them. And you can actually scale them based on demand. So you can duplicate containers, have like many containers to meet the demand of like people using your application. And it's also YAML. It also uses YAML, so it's gonna be useful when we need to version control it on Git. So why Kubernetes? It's to have a microservice architecture instead of a monolithic one. So you want a application that are made up of smaller modules instead of having a single massive code base. So each module can communicate to each other using APIs. So they can send HTTP requests to each other and communicate like that. And that's in contrast to sharing a code base and communicating through a shared code base. So this also means that each module, each portion of the application can be updated and scaled independently. So this is useful because different teams can develop and deploy components more independently from each other. They just need to know the API specifications. So it also means easier debugging and maintenance because technically your code base is going to be smaller. Well, overall it won't be smaller, but for each module it's going to be smaller than a single huge monolithic code base. So it's going to be easier to find the problems. So also, it's also useful because you can actually scale each module independently instead of just trying to scale a single monolithic application. So say your database needs needs more computing power or whatever, you can actually just upgrade your database only. You can update the hardware of the database only, because containers on Kubernetes can be run across multiple machines, and resources can be allocated based on each module's needs and demands. So now we're going to talk about the overall, like a single Kubernetes system, which is called the Kubernetes cluster. So in a Kubernetes cluster, you have the Kubernetes master, which is which controls the everything. So it's running the Kubernetes software that's controlling the deployment of containers and whatnot. And each node is either a physical or virtual machine. So you can actually distribute your load across multiple machines, virtual or physical. And the master node is what's running the Kubernetes master. So it controls the worker nodes. So that actually begs the question, how can we run Kubernetes locally if we only have one machine? So we actually use Minikube, which runs a single node cluster. So you don't actually need to have multiple machines. But in the enterprise context, to make a proof of concept or whatever, you may actually need to have multiple machines. So it's run on the it's run on Linux. Like basically everything is run on Linux. But if you have a Windows dev environment, you need a VM or WSL like Docker. So now I've been using the word container a lot, but usually when we talk about Kubernetes, we actually talk about the about pods. So pods are the um, Kubernetes unit that we play around with. So usually it's a single Docker container, but it could be multiple Docker containers. Um, you can duplicate pods by for if you need horizontal scaling, so getting more resources by running more instances of your application or your module. And this can be specified in the YAML file. Um, you deploy pods like any other Kubernetes resources, so in a YAML file, and each pod is has its own like network interface. So it has its own IP address, and it's a IP address within the cluster. So it's not actually like a local area network, a LAN IP address. It's just inside of the cluster. So then we actually have Kubernetes services. So that's another Kubernetes object. So this is to solve a problem that we have with pods. So pods are stateless and can be dynamically destroyed and respond. So that's a huge problem because this changes the IP address. So so what if it's not even a what if, for sure another pod is gonna depend on another pod. So you're kind of screwed if you can't reliably connect to another pod. So for example, a front end and back end pod within a Kubernetes cluster, and the front end communicates with the back end. How can it find the pod with the IP that always changes? So services allow for the abstraction of pods. So you don't need the IP address, you just need to know the service name. So it defines a set of pods and how to access them. So you would never actually access a pod using the IP address. You would access it using a service. And that service is going to route you to the proper pod. So now we have a Kubernetes deployment. So it's another object. So it provides a way to declare how pods are deployed. So for example, which image is used, how many replicas, so how many duplicate pods you want, how they should be updated if you need to deploy a new version of the image. Um, so since it's a YAML file, you you can easily automate and repeat the deployment of pods by just specifying all the configuration in the YAML file. So you could actually use the Kubernetes backend to update pods instead of using scripts with commands, which honestly is really, uh, which would really be tedious. And next, another concept is well, namespaces. So namespaces are basically a virtual cluster inside the cluster. So it scopes the name of resources. So as you guys have seen in the Docker container example, we actually specify which container we want to modify or run a command on using its name, not its ID. So it's useful to have a name that's scoped inside of a single namespace, so that other namespaces don't have access to it. Um, So any of the Kubernetes objects or resources previously shown can only belong to a single namespace. So you can't actually have like a single pod be in multiple namespaces. Usually it's all the most simple and common use is just to organize resources when it's in a large cluster. But from a security point of view, it's also to allow for role-based access control, so RBAC. So that's in case you want to grant a specific role to someone inside of a specific namespace and not other namespaces. And then the next concept is, or rather object, is the ingress. So ingress is to manage external access to a Kubernetes cluster. So it exposes HTTP and HTTPS routes from outside towards inside of services in the cluster. So instead of having to use the IP and like ports and whatever, you have you use port 80 and you can designate a path in the URL towards each service. So you can actually have you can actually pair the ingress with a load balancer to, as previously mentioned, scale dynamically the cluster based on demand. So now we'll move on to deploying the actual cluster. So on Windows, well, even on Linux, you would need Minikube. So you would have Minikube and Docker and everything for Kubernetes. And aside from that, it's the same as with Docker. You have WSL and a Linux distro. So now we'll move to the actual demo. Okay. I'll close this. Okay, so this is probably going to be a long one, but first of all, as previously shown, we need to pull the container that we want to use. If we don't have it in the library yet, but in this case, we already have it. And then we move to the directory where our YAML files are located at. So first, let's begin with a simple deployment. So actually, let's so we have the API version. So like the Docker file, we need to specify which version of the file which how we define the file, how we define the YAML, so we need to specify it. I'm just double checking if that's actually it, because I think but yeah, anyways, usually you would keep this the same anyways, so it doesn't matter. So the kind is which type of object that you run, that you want to deploy. So this is a deployment, but we'll see later that it could be something else. Metadata is basically just the name, labels. So it it won't really have much effect because we're going to use services anyways, but we're still going to name the pods something. So, well, we're going to name the deployment something. Um, so the specs is basically the specifications for the API that we're going to deploy. So we select the app and we give it a label, and inside of the pods spec we have a spec for containers. So we specify its name and we specify the image and we specify what port it's going to expose. So it's going to be port 8000. So that's the basic structure of a YAML file. But usually you can probably find a lot of examples online of YAML files. So it shouldn't, because there's really a lot of ways to deploy a Kubernetes cluster. You can have many more components than just this. So, but this is the basic deployment of a single API server. So we'll begin by deploying this. So the command is simple. Like Docker Compose, you can just simply apply the YAML file. So you just do it like this. Oh, my bad. So you need to actually start Minikube. Okay. So now that we started Minikube, we can apply it, and we can see it's a pod. We can see it's pod, but we can also see the deployments that we deployed. So now we actually want to access the pod from outside. So we'll not use ingress now. We'll use a node port. So node port is gonna expose the IP for the pod inside of the cluster. It doesn't mean we'll be able to access it from outside, but we'll use a Minikube functionality to be able to access it. So we'll begin by writing the command to expose it. And by the way, you can also specify how you expose it inside of the YAML. I kind of forgot to do so, but okay. So, oh, yeah, yeah. So it already exists because I did do this earlier today. So I'll begin by cleaning up. I think this is the command. Okay. So we'll do this again, and we can see the service right here. So as previously mentioned, that service is going to allow other pods to access your pod. and it's gonna immediately redirect like it's gonna route any other pods towards the correct IP. So now if we want to test this, we'll use a nifty minikube feature that allows us to expose this node port IP to outside the cluster. So we'll use, okay, I didn't write the name correctly. So in theory, this should work, but anyways, okay, let's hope this works. Okay, this is bad. Okay, so we have the welcome home that we had initially. I think I didn't use the correct image, but this is why we don't have the endpoint. So I'll fix this real quick. So we're using 0.3, so we'll move to 0.4, and we'll try again. Oh shoot, this is yeah, I'm taking way too much time, but okay, anyways, we'll skip this then. But everything should have worked. It just didn't use the correct image. For the ingress version, I'm gonna use the correct image. Yeah, okay. We'll clean everything up again. Delete. And now we'll deploy it using ingress real quick. So we'll enable ingress in minikube. We'll check if ingress is indeed activated. So we have our ingress nginx controller. And now I'll deploy the service for each pod because I didn't specify it inside of the YAML once again. So for this, I'll probably just copy and paste. Oh, whoops, I didn't. So we need to actually apply the YAML first. Okay, well, I don't know if it works, but okay. So actually, I forgot to run this command, but this actually installs all the ingress dependencies that we need. I'll probably add it to the repo after, but anyways, now we have our ingress, and hopefully this works. So I'll just double check if we have the services, and we don't. Oh, whoops, my bad. I'll just run these again. So we have the services. Okay, so now it should the ingress should be deployed. But since we're running in Minikube, we need to tunnel access to the cluster outside of Minikube. So, hang on. Okay, so now this should work. So we'll check this inside of Postman. I'll just double check first that. So now we have Nginx, and if we go to, so now we don't need the port because it's Nginx and it's at port 80. So that's the assumed port for URLs. So if we do this, we have the Nginx, and shoot, I forgot to explain how the ingress YAML works, but as shown previously, you can specify a path for each for the deployment. So we'll go back to the YAML because I kind of forgot to explain. So in the YAML, we have, as shown previously, we have one deployment, which is the exact copy of the other one, but we also have a second one, which is a second deployment of the exact same API. But now we have something special, which is the ingress object. So it's not a deployment, it's ingress. We have the metadata and everything. And we have the path, and we choose which service we want to route the path towards and the port. So we repeat this for path 1 and path 2. And this should translate into Postman as well. So if you go back, as I've shown, there's 1, but there's also 2. And we can also do the int storage thing, which doesn't work. Yeah, anyways. I guess it's probably an issue with the image or something. But that's the gist of it for Kubernetes, at least. And there's still another portion of the presentation. So I'll try to blaze through the rest. So now there's a useful software for managing Kubernetes deployments. So it's called Helm. So you could have the application with so many YAML files that it becomes a pain to manage. So say you have a service for the deployment of a database, plus the service for the deployment of a website, plus the service for the deployment of a Nginx. You're going to have a lot of YAML files or a lot of lines of whatever. And you kind of don't want to have a script to just deploy each one by one. So you can just package it into a YAML file, into a single Helm shot. So you can distribute them and run them using a single command, just like Docker Compose. So I'll actually not show how to create one because it's getting lengthy, but I'll just show a quick deployment of a a Helm shot. So it's actually super easy. I'll just quickly deploy HashiCorp Vault. So that's just a random software that's in the form of a Helm chart. So first of all, I pull a Helm chart from a remote repo and I just install it. So it's as simple as that. So now we have the Vault, which is the application we're running. And it also has a database and a whole file system behind it, which is in another namespace. But the point being that we just deployed a complex application with like 2 commands, so it's super easy. So now we'll go into a more, it's, I guess, theoretical maybe portion. So this is security in Docker and Kubernetes. So it's useless to deploy the application if anyone can access it or can just like if anyone can just break into it easily. So usually in a cloud security model, you have multiple layers to penetrate before compromising the application, and you and the inner layers security is complemented by the outer layers security. But each layer still needs to implement proper security practices. So the layers in this case is the cluster, is the cluster, um, and then we have the container which is inside the cluster, and then the code in it that's inside the container. So this helps to so we need to have good security for each layer of the application. There's also the cloud portion that I didn't mention. This is like Azure, AWS, which and the security for that one is basically up to them. But now we'll begin with the container layer. So we won't talk about code or like the AWS Azure security practices because that's provider specific. But um, but we'll start by talking about Docker content trust. So it's difficult to trust images and to see if they've been tampered with or not. So there's a feature of Docker that can allow you to secure that aspect of images. So we don't know if it's been tampered with in transit. So we want to attach a digital signature to the images, or rather the tags. Um, and those signatures will validate the integrity and the source of the image. So yeah, integrity and authenticity. Um, so how do we sign images? So the publisher of the image, which probably would be us or maybe someone else, um, which would generate a asymmetric pair of keys. So that's cryptographic keys with a public and private component. Um, so we're going to use them to decrypt and encrypt data during the signature process. So just a basic explanation of what keys are. So once you sign something with a private key, it can only be decrypted by the public key, and vice versa. So something that's encrypted with the public key can only be decrypted by the private key. So we'll use the private key to sign the image, and if the public key can decrypt it, then we can prove that we have the private key. And with the private key comes also our identity, so it proves our identity. So actually we'll need to talk about what is a tag. So it's a alias tied to image ID. But rather, what's a image ID? So the image ID is a unique string that 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 identifies a specific JSON configuration object for the image. So it's actually just the hash. of the JSON, and the hash is unique for each different JSON. So even if you have a extra white space, it's going to be completely different, not only by a single um, hex value, but by a single value, by a single character. It's going to be different on the whole image ID. So how does signing work? We encrypt the image ID using our private key, and we publish the public key to others so they can verify the hash. So how can you validate the image? You hash the JSON configuration object again, and you check if it's the same as this one, as this hash. So if it's the same, then it's good. And since that's the hash we encrypted, then it also means it came from us. So that hash cannot be replicated as previously mentioned. And and uh, and yeah, we hash the JSON configuration. And the user can decrypt the original signature to see if it's the same. So yeah, in a nutshell, we use the private key, and it's and we encrypt the hash. And after we encrypt the hash, the user decrypts the hash, and they check that the hash is correct, and that proves the integrity, so that nothing has been tampered, and it proves the authenticity, which means it came from us. So we'll do a quick demo of this, um, of of how to sign the image real quick. It's um, so we'll first generate a key pair actually, and we will protect it using a password. And we'll check which image we want to sign. So let's say we want to sign this one. So we'll just go real quick and sign this image. And using the key, we have it signed. But do keep in mind that if it's the first time you're running the actual command, you'll need to generate a few other keys. So yeah, it's going to be a bit long to explain, but basically you need to have other keys that validate the key that you're using to sign it. And it's a whole system, and that's and that's how we could validate uh, the um, the signature by having a key that only we have, and that proves that we indeed signed the image. Yeah, so we're almost done, but just a few other slides about other security practices. Oh, whoops. Okay, hold up. So if you pull a third-party image, do make sure that the content of the image is trustworthy using Docker content trust, and also make sure that it's not from a shady website or whatever, or a shady repository, I mean. Um, Control access to the Docker daemon. So control access to the Docker API and whatever, that all the commands that you can use to deploy containers, make sure that only you can use those commands, or only people you trust can use those commands. So by default, only root users can access it, but the problem is when attackers have access to the daemon, they can start containers that share the directory of the host. So say non-root users can access the daemon, you can have attackers actually access root directories on your host systems. So that's actually insanely dangerous, because you don't want non-root users to have access to your root system, your host system. So yeah, so definitely control the access to the Docker daemon, and also use um, use role-based access control, which I believe Docker has. I'm not 100% sure, but it should have it. Um, Also avoid exposing the Docker API over HTTP. So that's actually simple, because HTTPS is encrypted and all. So if you do it over HTTP, you're gonna leak your password, your certificates, and whatever other secrets that you have, which opens up a slew of attacks. So yeah, use Docker Content Trust. So now we'll move to Kubernetes security. So it introduces a new attack surface, so a new layer that you need to secure, as shown previously in the cloud native security model, like the 4 Cs. So um, you should use proper security practices on top of the other ones. It doesn't mean that you have a secure Kubernetes, doesn't mean that you have a secure like Docker or like container. So um, so you want to control access to the Kubernetes API. So the goal is to prevent random users from gaining access and doing wrecking chaos and whatever. So first use TLS, so HTTPS, anything. So it's going to encrypt your traffic, your password, and whatever. Oh, should I mess up the PowerPoint? Hold up. I'll just. Yeah, it seems like I messed up PowerPoint, but so first we have authentication, which is verify the identity of users. So we can use client certificates. So it's the same concept as the Docker Content Trust. You have a private and public key pair, and you can validate your identity using that. It's a bit more complicated than that, but yeah, you can use client certificates. You can use a bearer token, which is a randomly generated string that's been assigned to you so that you can authenticate. So it can be in a file, it can be in a HTTP request header as well. You can have a simple password, or you can have OpenID Connect. So OpenID Connect is a addition to OAuth 2.0. So it's basically just if you log into a I don't know if this one has OAuth, but yeah, it's when you log into a page and then you have like login with Google, login with Microsoft, or whatever. So that's OpenID Connect. Um, and those are the main ways of authenticating yourself. But you also want to have authorization, so controlling which user has access to which resource. So you have role-based access controls. So that's the one mentioned previously. Each role has a certain permission level, just like Discord. So say a Discord role, a moderator has permission to kick and ban people, but a regular user doesn't. That's because the moderator has a moderator role, which also gives them a red name, but that aside, they also have the ability to kick and ban people. So that's role-based access control. But you could also have attribute-based access control, which is really more precise than role-based access control. Uh, you can you can give attributes to the user and have resources that only grant access to a user that has a set of attributes. So you can have the attributes such as name, role, security clearance, location of the user. So say you could say that, hey, Russians can't access this or that, but that say Canadians can. You can also have a resource-based attribute, so the creation date, the resource owner, the sensitivity of the data. Or you could have environmental factors such as time of day and the location of the data or the resource that you're trying to access. So attribute is a lot more more granular, but it's probably a bit more complex to set up. And um, you can also lock people to nodes. You like some users can only access said nodes. So last slide. So you also want to control the capabilities of the workloads or the pods and resources, as well as the users. So you want to limit resource usage to not have, well, it's not that much about security, more about noise. So anyways, it's you could have a pod interfering with another pod, or maybe even interfering with like a security resource. So you want to limit resource usage as much as you can and scale them dynamically using load balancing. So you want to add a resource quota, like a CPU quota, a memory quota, a disk space quota, maximum pods or services for a cluster. Control the container's privileges. So pods can be allowed to run as Linux users on the node using like a security context setting. That could be useful in some cases, but it does give it dangerous capabilities because your pod is going to be able to do just wreak havoc and like even affect other pods. So use pod security policies to limit who can grant those security context settings, and otherwise also add network policies to limit how much pods can access other pods, because pods are technically accessible by any other pods like all the time. So as long as you have a service that identifies the pod. So you want to limit how much access they have, so you can use network policies. And control the nodes that pods can access. So if your pod doesn't need access to another node, don't give it access. So the whole gist of this page, this PowerPoint slide, is that don't give your pod like permissions or like anything else that they don't need. Limit it as much as you can. So you can use node selector to add a constraint on which node the pod can run in. And that concludes this lengthy tech talk. If anyone has any question, guys can let me know right now. Otherwise, I also want to show that you can go on the repo itself and add a discussion. Well, after this tech talk's done, like maybe if you have any questions for me, like way later, because I do know many people have exams, so it could be useful to just watch it later. So so
Yeah, I have one question. What's the difference between a container and an image? And then what's the difference between a pod and a cluster? And then what's the difference between a pod and a cluster?
wait, like, oh hang on, can you repeat?
Yeah,
Because
let me write it down. Actually, it's be easier.
and actually, holy crap, I think I didn't record.
No.
Yeah, my voice doesn't appear on the freaking YouTube
And what's the
stream.
difference between a pod and?
Oh man, why? My OBS is set up correctly. Like,
Rip.
fucking kidding me.
That happened to me too.
No, but it's not supposed. What the fuck? Oh, okay. Well, that sucks.
Typical.
Oh well, it happens in.
Wait, actually, this is not.
It's the first time.
Actually, it does appear, but it's really low.
All right.
That's okay. If it's slow, we can just boost the sound.
Anyways, just let me know the question and
Yeah, I wrote it. I wrote it in the chat.
Okay. Okay, so container vs image. So a container is the image being run, while the image is just like the disk storage of it's like a it's like the what can I call it? The stripped down OS. It's the libraries and everything all packaged inside of a file. So image is a file that contains like everything you need to run in a container. So as in contrast, the container is that image being actually run.
Okay.
So yeah, you can actually use the analogy of I guess the image could be like an exe file. And well, in analogy, it could be an exe file, and the container could be the process actually running on the computer.
Okay.
As for the pod vs node vs cluster, so the pod is the unit, the smallest unit. Well, not the smallest unit, but the second smallest unit. The smallest unit being a container that's inside of a pod, and the pod is inside of a node, and the node is inside of a cluster. So the cluster is a concept, that a abstract concept of a application or a mini service application. microservice application. So the cluster contains all the pods, all the everything, and the nodes are the actual machines. So you could have virtual or physical machines, and you can have many of them. You can have a dozen or hundreds spread inside of a data center, and you can use Kubernetes to spread out the pods inside of all these these machines. So the concept of node is just like one machine inside of the whole system, the whole Kubernetes cluster. I don't know if that helps.
So can you have more than one container in a pod?
Yeah, actually you can. I don't know in which case you would, but you technically can.
Okay.
But yeah, that's
Okay.
but yeah,
Okay.
I think honestly the Kubernetes concepts, those are probably a bit like those are super theoretical, but they do have like they do like you do need to know them if you use it in practice. So
Okay. Thank you.
no problem. And I hope it's actually my voice being super low and not OBS not recording, but we'll see.
Time will tell.
Actually, it most likely is. Yeah. Yeah, I guess also I super well structured my PowerPoint, but then kind of. Anyways, I'll end the stream first. But